got a PhD degree in 1982. And then he moved to IBM and stayed there for 11 years. And in 1994, he moved to University of California at Berkeley as a full professor. And how do I say, Professor Lee is one of the best condensed matter physicists in the world. And so today, he's going to talk about some interesting story in ion-based superconductors. So let's welcome Professor Lee.
Okay, can you hear me? Is this on? It is on. Okay, can you hear me? Okay, yeah. It is my enormous pleasure to visit Taida today and give a colloquium here. Taida physics was actually my dream, but I failed to enter it in 1974. Today is really a great pleasure to visit here, to see so many old friends. So my personal research, I'm condensed matter theorist. My personal research basically 50-50 divided into two parts. One part is unconventional high temperature superconductivity, and the other is a topological aspect of condensed matter physics. So today I choose the topic so that this actually intermingle between the two interests of mine. Although the title sounds like it is a material science problem, but it's actually not. Okay, so here are my co-workers. Fa Wang was a graduate student at Berkeley, and he's now a professor at Peking University, and Steve Kittleson is a professor at Stanford University. So today, the topic, you will see what it really is. And here is the outline. This outline intermingles between two main topics. One is I will begin to describe a concept called quantum disorder, and then I will describe phenomena related to ion-based high-temperature superconductors, and then I will come back to talk about why quantum disorder has anything to do with ion-based superconductors. I will not go through the outline one by one, but I hope it will be clear in the talk what I'm talking about. So first, let me start it by describing the concept of quantum disorder. Lev Landau was the first who proposed that the order of a material is associated with the spontaneous symmetry breaking. For example, well-known example, we have water freeze into ice. If you imagine yourself sit at the center of a water droplet and you look in all different directions, you find all the directions are equivalent. So you have directional isotropy when you sit in the middle of a water droplet. However, if you sit in the middle of an ice cube and you look around, you will not find every direction equivalent to each other. So in other words, water, which is less ordered than ice, but water actually has higher symmetry than ice. Namely, the directional isotropy, the directional equivalence has been spontaneously broken when we come to ice by just lowering the temperature. Another textbook example is the paramagnetic to ferromagnet phase transition. We know you take a piece of iron, if it is above the Curie temperature, then the local magnetic moment in iron is completely disordered. And if you look at the so-called Boltzmann weight for realizing each different pattern, it has spin rotational invariance. But once you lower the temperature to lower than the Curie temperature, then those magnetic moments will spontaneously align, and then this rotation symmetry of the magnetic moment is spontaneously broken. Again, paramagnet is less ordered than ferromagnet, but however, it enjoys more symmetry than ferromagnet. So this is another example of spontaneous symmetry breaking. We all know the idea of spontaneous symmetry breaking is so important and is so ubiquitous in nature that it can exhibit itself in the daily life. Water freeze into crystal, or normal fluid going to superfluid. It even happens at a much granular scale, namely the magnetic state of the neutron star, and even it is an essential concept for us to understand the expanding universe. So the idea of spontaneous symmetry breaking and order influence condensed matter physics, if not all the area of physics, so deeply that it is very hard actually to find a system which remains completely unordered in any way. Namely, the system remains quantum disorder. That's what I mean by quantum disorder. The symmetry has no symmetry breaking whatsoever, even when you lower the temperature to 0. It is very common that at high temperature the system will not break any symmetry and remain disordered. But it is extremely unusual that even when you lower the temperature to 0, the system still remains unordered. So now I want to switch gear to talk about a seemingly totally different subject. Okay? This has to do with high temperature superconductivity. This is a famous historical plot of the critical temperature of superconductor versus time. And there are 2 milestones. The first occurred in 1986 when Bennos and Mueller discovered the copper oxide high temperature superconductors. Now at the ambient pressure, the highest transition temperature is achieved in the mercury compound is 135 Kelvin. Very recently, quite recently in 2006, Hosono discovered a new family of high temperature superconductors, which are known as the ion-based superconductor. And its critical temperature has been now elevated to extremely close, if not above, the liquid nitrogen temperature. And this highest TC compound is iron selenide, a single atomic layer of iron selenide deposit on dielectric strontium pattern. By the way, iron selenide was discovered in Taiwan by Malcolm Wu in the bulk crystal form. So this fact really single out iron selenide as a very special compound. So now I would like to explain to you what does nematicity mean. Okay, so just like cuprate high temperature superconductors, there are many members now of ion-based superconductor, but they all share a similar phase diagram. If you plot a doping, chemical doping versus temperature phase diagram, the system has a magnetic phase, antiferromagnetic phase, and followed by a nematic phase, and then followed by high temperature superconductivity. So what do I mean by the antiferromagnetic phase? So here, the the red and the blue arrows indicating the direction of the local magnetic moment. Unlike the copper oxide high temperature superconductors, this ion-based superconductor has a different magnetic state. If you look at this pattern closely, you will find that the magnetic moment aligns, in this case, in the vertical direction, but anti-align in the horizontal direction. And this type of magnetic pattern is called a stripe magnetic pattern because it consists of ferromagnetic stripes and align anti-ferromagnetic. If you raise the temperature, okay? If you raise the temperature, for example, let's say we fix the doping and raise the temperature and cut through the phase diagram like this, you will find that this antiferromagnetic order is destroyed in this green region. In this green region, what happened is that experimentally, the lattice structure spontaneously distort. And due to this, so originally the lattice has a square symmetry, but after the spontaneous distortion, it becomes to have a rectangular symmetry. So this lattice distortion, very interestingly, it doesn't break any spin rotation symmetry. By spin rotation symmetry, I mean rotating the direction of the local magnetic moment, because the antiferromagnetic order has been lost once we enter into the green region, but yet this region has a different symmetry breaking. It destroyed the crystal 90-degree rotation symmetry, not spin rotation, okay? Crystal rotation is different from spin rotation. So if the crystal spontaneously distort from square to a rectangle with the long axis in the x direction, it obviously has broken the 90-degree rotation symmetry. And this nematic state is a phrase that borrowed from the study of a liquid crystal, and it means that it is a state without translation symmetry breaking, but with the rotation symmetry breaking. Okay, so this is what we mean by nematicity in ion-based superconductors. So as you can see, for all different types of ion-based superconductors, they all have the three different phases, namely the antiferromagnetic phase, and the green region is the nematic phase, and then the superconducting phase. So the main message of this slide is that the nematic phase is ubiquitous. It's not a exception, but it's a rule in ion-based superconductors. So like any mechanism in any high-temperature superconductor concerning any phenomena, the mechanism always has a debate. So here, the debate is what's the mechanism, what's causing the nematicity. I'm not talking about what's causing Cooper pair, okay? I'm talking about what's causing nematicity. And you might ask, why does that matter? Don't we only care about what's causing Cooper pairing? But wait, I will explain to you why is this a relevant issue. So when we talk about what's causing the nematicity, there are two schools of thought, and currently they are debating with each other very fiercely, and there are two schools. One says that the nematicity is caused by a magnetic mechanism. The reason is very simple, because in the phase diagram I show, when you lower the temperature, the system eventually becomes magnetic ordered. For example, this was the picture I showed before. You have spin ferromagnetically aligned in the vertical direction and antiferromagnetically aligned in the horizontal direction. Of course, such a magnetic pattern not only spontaneously break the spin rotation symmetry, but also it breaks the crystal rotation symmetry. Because if you rotate this pattern by 90 degrees, it becomes this pattern, and they are not equivalent to each other. And here, the ferromagnetic alignment is in the horizontal rather than in the vertical direction. Okay, so the magnetism school has a very secure foundation, because they just based on the rotation symmetry breaking is ultimately connected to the fact that the ordered state, the magnetic ordered state, also break the rotation symmetry. Now, the other school, to talk about the other school, I need to tell you a little bit about the quantum chemistry. When somebody tell me about quantum chemistry, I will find, my God, this is a dirty problem. So I try to not to listen to them. But this is actually quite simple. It turns out that in ion-based superconductor, here the blue ball represent a ion, and those 4 orange balls represent selenium or arsenic or whatever, and they form a tetrahedron. Okay? So because of the each ion has valence electron in the 3d orbitals. Each d orbital has 5 energy levels. If this ion atom were in a vacuum, so all those 5 energy levels should be degenerate with each other. But since it actually lives in this tetrahedral environment, those 5 energy levels split. Okay. So what happened is that in the if there's no chemical doping, each ion has 6 3d electrons. So the 2 lower level each accommodate a spin up and spin down, totally 4 electrons. And the upper 3 levels, okay, in fact, you probably have learned in modern physics that there's a rule called the Hund's rule. In the Hund's rule, it says that when an atomic shell is open, then actually the magnetic moment like to align with each other. So, but in this case, there are 2 possible occupation patterns, and these 2 occupation patterns differ from each other. But which one of the topmost 2 levels do I occupy? You probably cannot read it, but this is the dxz orbital, and this is the dyz orbital. So if I choose to occupy this pattern, then xz and yz symmetry is spontaneously broken. Xz and yz, if it is spontaneously broken, that means a 90-degree rotation. Because if I rotate xz by 90 degrees, it becomes yz. So 90-degree rotation in this school is caused by such a breaking of the occupation degeneracy, and that's called the orbital mechanism.
So those states are degenerate.
Those states are degenerate, are indeed degenerate. So, so now it comes to the question, why does it matter? Don't we want to understand Cooper pairing? Why do Cooper electron pair at such a high temperature? Why do we care about this this side phenomena, nematicity? The reason that we care about this is because of the following. Just like in high energy physics, when we look at the low temperature physics of a material, we are looking at the effective Hamiltonian of the system at low energy. Okay? So the you can write down the highest energy Hamiltonian. Our particle physics colleague often say that there's nothing to be learned from the high energy physics, because we all know, electron interact with each other with Coulomb interaction and attract with ionic core with the Coulomb interaction, so everything is understood. But the problem is that what happened at very low energy. So those high energy Hamiltonian evolve into the low energy Hamiltonian via very, very non-trivial processes called renormalization. And the question is that for those high temperature superconductors, what is the low energy effective interaction? It's only after we understand what's the nature of this effective interaction, then we know why electron will pair up with such a strength. Because superconductivity, no matter how high temperature, is a very low temperature phenomena, at least at this moment. So now you can see that, so why do we care about what's causing the nematicity? Suppose nematicity is proven to be caused by the orbital interaction rather than the magnetic interaction, then we know, at least we have a strong hint, that this effective interaction that we are going after is actually involved the orbital degree of freedom. That's what we call the orbital fluctuation. But if what's causing the nematicity is the magnetic mechanism, is the spin mechanism, then we have a very strong hint that what's causing the Cooper pairing is the magnetic interaction. So that matters, okay? That really lies in the heart of high temperature superconductivity. That's why we care to investigate the nematicity at all. Are there any questions? Okay, good. Oops. Why does this repeat? Okay, so now I come to this. So yeah, right. Sorry. So let me go back to the phase diagram. You see, in the magnetic mechanism school has enjoyed tremendous support because even you look at the phase diagram, you immediately see the nematic state happen next to the magnetic order state. So this immediately tells you that the magnetism must have something to do with the nematicity. So the magnetism school has been enjoying, has been abusing the orbital, fluctuation guys, and say, look, isn't that obvious? It is the magnetic mechanism that's causing the orbital order. Everything is really good until this compound discovered by Wu Maokun in Taiwan. This compound, as far as superconductivity is concerned, very few people are interested in it because it has a very low superconducting transition temperature, only 8 Kelvin. Okay, so if you want to have a high temperature superconductor, you want to avoid this material. But this material, however, behaves exceedingly unconventionally, unlike all the other ion-based superconductors. And here is the phase diagram. Vertical axis is temperature, and the horizontal axis is pressure. Let's don't worry about the pressure. Let's just put pressure equal to 0, ambient pressure. Okay. So at ambient pressure, when you lower temperature, the system, this solid line represent the structure will spontaneously distort from a square to rectangle. So that means the system, the 90-degree rotation, crystal rotation symmetry is spontaneously broken here. But the neutron scattering study has told us that below 90 Kelvin, here is the 8 Kelvin superconducting transition. Below 90 Kelvin, there's no magnetic order whatsoever. Not only the magnetic order state is not close. The magnetic phase transition, not only it is not close to the structure phase transition, there is non-magnetic order state. So at this point, the orbital school really revived. They say, look, this clearly is telling you that magnetic interaction has nothing to do with nematicity. You might argue, wait, but this is not fair because it is only one material. For all the other material, it is not like this. But in science, if you establish one case in which nematicity is caused by orbital fluctuation, that forces you not to ignore the orbital fluctuation for all the compounds. Okay, so this becomes, at this moment, the most debated issue in ion-based high-temperature superconductivity, namely what's causing ion selenide to spontaneously distort at such a high temperature and with no magnetic order whatsoever.
Excuse me. So the TS is measured by X-ray or?
The TS can be measured by neutron scattering also, and also can be measured by X-ray. You just see whether the peak split or not. Okay, the situation is even worse than that. Not only there's no magnetic state, but the NMR, nuclear magnetic resonance, which probe very low energy spin fluctuations. Okay, this is a probe which probe very low energy fluctuation, and this is a quantity which experimentalists measure is 1 over temperature times the lifetime of the NMR line. You don't need to understand the detail, okay? So what happened is that for all the ion-based, so here, the red circles represent ion selenide, and all the other symbols represent other ion-based superconductor, and this black arrow indicates the temperature at which the system spontaneously distorts. So as you can see, so the only thing you need to know is if 1 over T1T is very big, that means the system at the low energy has a lot of spin fluctuations. So here, as you can see, for all the other ion-based superconductors, when the nematic spontaneous structure distortion happens, the 1 over T1T is already substantially enhanced relative to the high temperature state.
What is T1?
Huh?
When you say 1 over T1T, there are two T. 1 T1, the other is T.
T is temperature. T1 is the width of the NMR line. Is 1 over T1 is the width of the NMR line. So now, however, for ion selenide, here is where the structure transition occurs. Not only the magnetic fluctuation 1 over T1T has not been enhanced here, but it is a minimum here. Okay, it's only below the structure transition it begins to be enhanced. So at this point, there's no doubt among experimentalists that this system is actually driven, the nematicity is driven by something other than magnetic fluctuations. So we see many papers stated that we definitively prove that ion selenide nematicity is caused by orbital fluctuations. So at this point, really, the orbital fluctuation school has enjoyed utmost glory, and they claim that actually all the high temperature superconductivity in ion-based superconductors is also caused by orbital fluctuations.
So my question is, can orbital, can really calculate how they change from square to rectangle?
Right.
Dimension-wise, you should be able to calculate, right?
You are absolutely right. But one thing in condensed matter physics, unlike you guys, okay, to quantitatively predict something is extremely difficult. To qualitative, unless the quantity we try to predict is universal, such as critical exponent.
It's a simple system. Ion and selenide.
No, it's a very complicated system. It actually has 5D band. Okay, it's actually quite complicated. But you are right. In ideal world, we should be able to predict.
That's why I thought it should be.
Yeah, should be able to predict.
Especially with this kind,
I know.
supercomputers.
I know.
Put every case in there and calculate.
Okay, that's not true actually. In many body physics, the problem is that those systems has a strong electron spectrum interaction, which I didn't talk about. And in many body systems, the Hilbert space dimension grow up exponentially with the degree of freedom. Therefore, brute force diagonalization is impossible for many body physics. For one body physics, such as band structure, it can be routinely done. But for many body physics, it cannot be done. Okay, so the gear now is switched back to talk about. So I've talked about quantum disorder. Namely, quantum disordered systems are systems which even at 0K, it does not break any symmetry of the Hamiltonian. All the symmetry of the Hamiltonian still exhibit at t equal to 0. Okay, and that's a quantum disordered state. And then I talk about this phenomenology about ion-based superconductors. All the different ion-based superconductors, they basically share the same phase diagram except one. Okay, this ion selenide. So that exception make us deeply wonder what's causing Cooper pairing in this ion-based superconductors. So now I talk about quantum paramagnet. So first, I define what do I mean by quantum paramagnet. Quantum paramagnet is related to quantum disorder because a paramagnet is a disordered state of a magnet. Okay, quantum paramagnet is a magnetic system whose spin degree of freedom remains quantum disorder. That is, there's no spin rotation symmetry breaking down to t equal to 0. That's what quantum paramagnet means. Okay. Historically, in '87, the notorious Phil Anderson proposed an idea of a quantum paramagnet called the resonating valence bond spin liquid. And he proposed this as the parent state of another family of high temperature superconductor, which is the copper oxide high temperature superconductor. So now let me just briefly explain to you what his physical